Hello, my name's Holly Andrews from Chalmers University of Technology, and I want to thank the GAPS 2021 organisers for allowing me to give a brief talk highlighting some of the results we have looking at the molecular content of the outflows of the red supergiant NML-SIG. So NML-SIG is a late M-type red supergiant located about 1.6 kiloparsecs away within the Cygnus X region. It has a relatively cool temperature of about 3,300 Kelvin and a high luminosity of a few 10 to the 5 stellar luminosities. So typical characteristics for a red supergiant. One of the most important factors of red supergiants is their high mass loss rate. For NML-SIG, this reaches up to around 10 to the -4 solar masses per year. And this leads to having a rich circumstellar environment, which will contain all this material that is thrown out from that star. So one of the things that we can do is look at this star using radio observations to check out its molecular line emission, and this can tell us more about the chemistry and its stellar wind and outflows. So the observations I'm going to talk about briefly today are secured from the Onsela 20-meter single-dish radio telescope back in 2016, where an unbiased spectral scan survey was carried out at millimeter wavelengths, looking from 68 to 116 gigahertz. And we were also able to then include the consideration of transition lines from other transitions from the molecular species we detected using published data from the James Clerk Maxwell telescope and also Herschel's HiFi instrument as well. So the observations we have from Onsela actually led to new detections for 15 molecular emission lines from 10 molecular species down to a noise sensitivity of around 5 to 10 millikelvin for the main beam temperature. And this actually included the first detection for H13CN found from its ground state rotational transition. Other lines that were detected came from typical species that we would expect for red supergiants. So this includes sulfur-bearing species like SO and SO2, and silicon-bearing species like silicon monoxide and its isotopologues. So here we have an overview of the different molecular line detections that we have from Onsela. And this is very, very crowded, but basically what we found when we first looked at these different line profiles is that systematically there was more blue shifted emission than we might expect for a simple spherical wind. So we decided to take a closer look using a first approximation of a multi-component fit. And this basically consisted of 3 different Gaussian components being fit to each of our molecular lines. So here we have blue Gaussians for the blue shifted emission, yellow in the center for a central component, and red for a red shifted directed outflow component as well. And we're able to combine these together to create our overall profile fit in purple, which you can see in each of these plots, as well as the residual plots underneath. And we also have vertical dashed lines indicating the central or mean velocities of each of our Gaussian components, which I'll go back to. So I don't have time to go into detail of all the different molecular line detections that we have, but we were able to bring in those previously published data and look at different transitions for the molecular species that we had. This included molecular species such as here we have carbon monoxide, where you can see that multiple components fit well to broad profiles. And we also had to deal with interstellar emission and absorption, as indicated here, contamination that we were able to mask out for our final line profile fits. We were also able to look at a silicon monoxide, where we could compare what we saw for thermal molecular line emission, as well as here we have an example of a maser detection that we detected with the Onsela observations as well. And as you can see, it doesn't quite fit the 3 different components as well as our thermal molecular line emission does. This is likely because these different types of molecular lines are tracing different regions of the outflow. And we were also able to look at water lines as well from previously published data, where you can see that there's contamination from ISM absorption as well as a maser line as well. So the main result was that we found that in general, we do find a good multi-component fit for all our molecular lines across the different molecular species. But also going back to those mean or central velocities that I mentioned earlier, we actually found that the mean velocities of our red shifted and blue shifted components decrease with excitation strength. And we believe this is because the higher excitation transitions are actually tracing inner regions of the wind that haven't been fully accelerated. So there are some approximations inherent in this simple fit. So we just use 3 Gaussians as a first fit to the data, and also some of our data points, some of our species only have a small number of data points. And if we were to do this more in depth, we need to account for things like optical depth effects. So we hope future studies will actually use spatially resolved observations to better constrain regions that are traced by these different components we believe to be present. And actually, we're currently in the process of reducing and analysing NOEMA observations that we secured earlier this year, where in fact we have here just some preliminary channel maps from carbon monoxide showing that there's already clear evidence of these different asymmetries in our spatially resolved observations. We actually see differences across the molecular species. So here's my summary slide. We detected these various lines and found evidence for multiple components in the outflow, but there really is a need for more understanding of the complex environments around these classes of stars. And if you do have any questions, please do reach out to me at my email address.